So another part of rate of change is linear motion. So what is linear motion that we're talking about here? Linear motion is the motion along a straight line, usually horizontal or vertical. That's exactly what it sounds like. We're moving in a straight line, so either up or down or left or right. What we want to think about, though, is that what is the derivative of position? So the important part of linear motion is that what is the derivative? The derivative of position. Well, let's think about it. If S of t is position, so this says what is the position again away from your starting point. What are some units of S of t? This could be something like meters or feet or, I don't know, miles, any sort of distance. What is the derivative of this, where t is measured in time? So the derivative of S of t, those units would be mile per maybe seconds, or feet per hour, whatever time is being measured in, or mile per minute. These are all units of velocity. So what we're going to take away from linear motion, this is kind of the big idea behind it, is that the derivative of position, so S here is position, is velocity. So if we have an equation for position, and I want to find velocity, all I do is take the derivative. So this is another way that we're going to use the derivative, and that is to find velocity from position. Okay. Can velocity be negative? Absolutely. That just means that I'm moving either in a downward motion or a leftward motion, so velocity can be negative. If you want to talk about speed, that's not the same as velocity. Speed is the absolute value. So speed is the absolute value of velocity. So velocity can be negative. We can talk about moving towards the ground, or we can talk about moving to the left, or some sort of negative direction. Speed is the absolute velocity of that, so speed can't be negative. So let's do an example involving position and velocity. Let's say the height of a helicopter. Height here is being measured in meters. The height of a helicopter at time t. T here is being measured in minutes. Is given by S of t is 600t minus 3t cubed for t between 0 and 12. So we have a helicopter. I have an equation that tells me the position of the helicopter for 12 seconds. Okay, so part A here is I want to graph the position and the velocity. So let's graph S of t and V of t. Well, I have an equation for S of t. S of t was 600t minus 3t cubed. So you could use your calculator if you want. It looks something like this for the first 12 seconds. So here's t, and this is measured in meters. So that's my height. What this says is that the helicopter first starts on the ground, so position's at 0. The position rises, kind of levels out, and the helicopter kind of goes back towards the ground. So this is linear motion. It doesn't look like linear on the graph, but what the helicopter is doing is just rising, and then it's coming back down. It's just going up and down. This is the position from the ground. The reason it doesn't look linear is because we're measuring it over time. What's the velocity? Well, we just said that velocity is the derivative of position, so I'm just going to take the derivative. So 600 minus 9t squared. What happens when I plot this? Let's see, that's going to be a parabola, something like this. So there's my v of t. So there's the velocity, here's my position. So I've just plotted the two graphs. Part B of this, what is the velocity when t is equal to 8? Remember, this is in minutes. So if I want the velocity when t is equal to 8, all I have to do is plug in 8 into my function. So I'll get 600 minus 9 times 8 squared. And what is 600 minus 9 times 8 squared? Let's plug that into our calculator. So we'll get 24. What are we measuring this in? Remember, this is the change in position over time. So this is going to be meters per minute. So the velocity when t is equal to 8 is 24 meters per minute. What that means is that 8 minutes into the flight, the helicopter is leaving the ground, so it's still rising because the velocity is positive, leaving the ground at a rate of 24 meters per minute. Part C, what is the velocity when t is equal to 9 minutes? Well, this is just plugging in 9 into our equation, so that's going to be 600 minus 9 times 9 squared, which is negative 129 meters per minute. So that means that when the time is 9 minutes, the helicopter is moving towards the ground. So this is negative, that means I'm moving towards the ground at a rate of 129 meters per minute, so that's very, very quick. So positive means I'm moving away from the ground, the position is increasing. Negative says that I'm moving towards the ground, the position is decreasing. Last question to ask here. When does the helicopter reach the maximum height? So when does the helicopter reach the maximum height? If we go back to our picture of height, or the position here, here's where I reach the maximum height. I'm looking for what is that t value. Okay, hopefully we can see that's the question that we're asking. Here I reach maximum height. I want to know what's that t value. Well, what do you know about the velocity at that t value? The velocity there is 0. Right, the slope of the tangent line is 0. And it kind of makes sense that the helicopter rises up into the air, and for a split second, there's 0 velocity because I went from going positive velocity to negative, so I had to go through 0. So it's really asking the question, when was the velocity 0? Because at this point, the velocity was 0. So I need to figure out, when is v of t equal to 0? Well, v of t was 600 minus 9t squared. Let's set that equal to 0. This will be 600 is 9t squared. Divide both sides by 9, so t squared is 66.6. Take the square root of both sides. T is about 8.165. That tells us, remember this was in minutes, tells us that the helicopter reached its maximum height after 8.165 minutes. That's how long it took. What was the maximum height? So how far up in the air did the helicopter actually get? Well, we know when it happened. All I need to know is what was the actual position there. So if the maximum height occurred whenever t was about 8 minutes, and I want to know what the maximum height is, that says I should plug in this t value into my position. So I'm going to plug this in, so this will be 600 times 8.165 minus 3 times 8.165 squared, about 34.53 meters. So we found when the maximum height occurred, but the actual question of what is the maximum height said I should plug it into position. So maximum height occurred here. What was the actual position? I just plugged it into the equation for position. So what to take away from this? Velocity is the derivative of position, and that's how we're going to use it. We're going to use this over and over. To find velocity, take the derivative of position. To find the maximum height or minimum also, that's going to be where the velocity was 0. So we're going to take the derivative, set it equal to 0. And to find the actual max height, you got to go back to the position.